PWT software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Mohammed Shah with you. Today we are going to talk about the concept of geothermal desalination system, especially if we are going to combine geothermal energy with any load, any desalination loads, such as reverse osmosis plant. What is the main concept? What is the approved geothermal technology that we can handle? How can we run our model? Okay, the main concept is that geothermal energy is electricity generated from geothermal energy. Geothermal energy is thermal energy generated and stored in earth. Technologies in use include dry steam power plants. Geothermal electricity generation is currently used in more than or around 24 countries, while geothermal heating is in use in 70 countries. Okay, estimates of the electricity genetic potential of geothermal energy vary from 35 to 2000 gigawatts. Current worldwide installed capacity is around 10,000 megawatts, with the largest capacity in the United States of America, Philippines, and Indonesia. Geothermal power is considered to be sustainable because the heat extraction is small compared with Earth's heat content. Okay, people have made use of geothermal energy in the form of hot springs for countries for centuries. However, the first attempt to generate electricity from this energy source didn't occur till the 20th century. It's simple. The concept is simple. Just hot rocks, underground heat water to produce steam. We can drill holes down to the hot region. Steam comes up, which is purified and used to drive turbines, which drive electric generators. There may be a natural groundwater in the hot rocks anyway, or we may need to drill more holes and pump water down to them. The first geothermal power station was built in Italy, and the second was in New Zealand. Others are in Iceland, Japan, Philippines, and United States, of course. The volcanic behavior in countries with volcanic behaviors. In Iceland, geothermal heat is used to heat houses as well as for generating electricity. As you can see here, there is a schematic draw of geothermal system. There's a reservoir and pumping house, heat exchanger, turbine, production well, and this is the injection. It varies from 2,000 up to 10,000 meters to the core of the earth. Okay, geothermal technology. Geothermal power stations are similar to other steam turbine thermal power stations. Heat from Earth's core is used to heat water or another working fluid. We can use another fluid, pentane, toluene, for example. Working fluid is then used to turn on a turbine or a generator, thereby producing electricity. The fluid is then cooled and returned to the heat source, to the ground. We have three main configurations. We have dry steam power plant, we have flash steam power plant, and this technique we are going to talk about today. and binary cycle if we are going to use a heat exchanger as an intermediate or a storage system. Okay, for dry steam plants are simplest and oldest. They directly use geothermal steam of 150, around 150 or greater, to turn on the turbine unit. As you can see, hot water or the steam is directly forced to power on the turbine units in order to generate electricity. The system is simple. If we considered the well as a unit, thermal source, it is one unit, turbine is the second one, generator is the third, and the condenser and pump and the injection is the fourth unit. Okay, the flash steam power plants, that's our main concept today. Flash steam plants pull deep, high pressure hot water into low pressure tanks and use the resulting flashed steam to drive turbines. They require flow temperature of at least 180 degrees, usually more, around 200, 230. This is the most common type of plant that in operation today. This is the same concept, but we have to put intermediate unit. It's a flash cyclones unit. There is no need for dry steam, just hot water, and there's a pressure difference. And this cyclone unit is responsible for generating steam as a flashing steam in order to generate turbine units, and the same cycle will repeat again. For binary cycle, we have to put intermediate unit instead of flash tank. We are going to replace flash tank by heat exchanger unit, and this concept is quite interesting for organic Rankine cycle operation, if we are going to use another working fluid and so on. Okay, let's go for our model. For our model, we have to consider the following. We have this is a well, and this is our flash tank, steam turbine, surface surface condenser, reverse osmosis as a load. Sure, you can remove this block and you can put just in Simulink you can put a constant block and type your load. Yeah, I mean, if suppose we need 1 megawatt, 2 megawatt, as you wish. We have to. I mean, we considered a new technique of such technology by considering concentrated solar gas engines, Stirling or Brayton engine, as a source of power to drive on the pumping system. This is interesting. We are going to discover how much power we can use. Okay. What is the reverse osmosis design aspects? What is the thermal plant design aspects? What is the area of the dishes that required? It's quite interesting system. Let's go and talk about this. To download your model, you have to specify your location, destination folder. Okay, and run your model. Okay, your model should be appear like this. Okay, double click on this. You can get some information or go to the video link or something like this. Okay, as you can see here, this is our the TS diagram. This is this point is inlet hot water from the well, and this is the flashing. This is the flashing process, and this is the steam generating goes to the turbine unit at point 4, and part of the flash will not surely it is remaining like some water, because we have a dynamics fraction percentage here. We have water and steam quality. So, and this is a condenser operation, extraction through the turbine unit, and this is the condensation. Okay, let's go and see how can run this. Okay. As indicated before, we have the following. It's a design model. I mean, we have to assign productivity and efficiencies, and the system will calculate flow rates, areas, and design aspects. Okay, it's suitable for future projects and reports and so on. This is reverse osmosis. We are beginning from the end, and this is our TS diagram process. As you can see here, there is input hot water. This through the flashing tank. So therefore, we have steam and water. The steam goes to the turbine unit, part of it, and the rest will accumulate in the accumulation tank. And this is a turbine unit, dry saturation, and this expansion through the turbine unit, and this is a heat rejection process through the condenser unit, and so on. Let's go for the reverse osmosis. I suppose we are not going to talk about deeply about reverse osmosis because we have many videos about this one. Okay, I am going to choose, for example, the reverse osmosis basic configuration. This ambient temperature, this salinity profile, salinity of the seawater, intake seawater. I'm going to suppose I'm going for 3,500 meter cube per day. I think we can choose our for seawater. I'm going for seawater 30 heat recovery ratio. I think this will consume around 39 or 38 elements per pressure vessels. We have 7 pressure vessels. I will keep this. This is a recovery ratio. I think it's for seawater it's 30% recovery ratio, and this for pill-to-wheel turbine and pressure exchanger. It is adjusted. Okay. Okay, let's see for condenser unit. We are just stabilizing our inputs in order to measure what is the aspects, design aspects. Okay, for performance, I will consider 80% heat exchanger. This is cooling. Okay, this cooling water temperature. This cooling water is seawater temperature because it will go through the condenser for heat rejection process, and it will bump it again for the reverse osmosis. This is a connection between reverse osmosis unit and two passes surface condenser. Okay. This okay, 15 degrees Celsius, I think, and this is outside diameter for the tubes. It's okay for this. Okay. Okay, for concentrated solar gas engine model, it's quite interesting model. We have a video about this one. Okay, I'm going for top cycle temperature for suppose it 700 degrees Celsius. Lower temperature 25, ambient temperature, operating conditions, this operating hour, ambient temperature, solar radiation, it's okay. If you have to choose between a Stirling engine or Brayton engine, it's up to you. I'm going for Stirling engine because it's the most efficient one. We can go to use I think carbon dioxide. It's up to you as a researcher. You have 12 working gases to deal with. It's up to you. You can measure this one, and we have published work about this. Okay, I'm going to choose CO2, okay, or nitrogen, for example. You have to, okay. Rim angle, I think it's 30, 37. It's quite good. Stirling engine, okay. Operating conditions, Stirling engine. Okay, the power developed by one dish is around 25 to 30 kilowatts. Okay, and this design limits, I keep it. As Brayton, there is no, we don't need to specify anything here because we are using Brayton engine. For performance, this is mirror efficiency, receiver efficiency, dish mirror efficiency. It's okay. I'll keep this. Acoustic considerations. I'll keep it. Okay. For pump, it's okay. It's efficiency 75%. Okay. I'm going for the well, geothermal well. What is quite important here is just to steam pipe diameter in inch, 5 inch. It's okay. Okay. And these two units are quite interesting: flash tank and turbine unit. For turbine unit, you have to specify the efficiencies of generator and the turbine efficiency. Okay, this is the power from the grid. Suppose you need to assign or to generate more power. Suppose I'm going to generate around let it be 3 megawatts besides the load from reverse osmosis. It's okay for you. If you would like to assign, just keep it at 1. Okay, but I'm going to generate 3 megawatts besides the load from reverse osmosis as a power for the main grid and so on. Okay, this is turbine unit. For flash tank, flash cyclone tank. Okay, we can assign here the turbine pressure. Okay, I keep it at 9 bars. Okay, and the condenser pressure, you can assign the condenser pressure. We are going to discover this effect as steam velocity. This effect on steam velocity is from 2.5 up to 45 meter per second. Is responsible. This parameter responsible for the height and the width of the flash cycle itself, because it's ability to the designer to decide which is the diameter, what is the diameter, what is the width, and so on. What is the height of the cycle and so on. Okay, I'm going for 9 bars, and the condenser is for 0.6 bars. Okay, let's go and hit run and see. I'm going for reverse osmosis section. This is our reverse osmosis section. You can go inside. You have basic that we are going to deal today. Built-to-wheel turbine and pressure exchanger unit is a little bit complicated and will take much time to talk about. Okay, let's go for this one. We assign the productivity here. Okay, and we are going to see our result. We have to watch the pressure. This parameter is quite interesting. Let's hit run. Okay, it's 59 bar. We have to deal with 69 bar. So I have to return back again. I'm sorry, return back and going for reverse osmosis. I have to decrease not water. I'm decreasing the number of pressure vessels. Let's see. I'm going for 35 elements and hit run. Okay, 61. Let's go back. It's just a trial error. I'm going for 29 elements. Let's see. Okay, 66 bar. It's 1 megawatt. Specific power consumption relatively high, but it can work. Sure, you can discover what is your needed mass flow rate, what is the brine mass flow rate, salinity of the brine, salinity of the distillate product. This is quite interesting. Some exergy of the feed, exergy of of the brine, exchange of the distillate, and so on. Okay, let's go for our plant. Okay, let's go here. Let's discover our results from the geothermal well. Number one. Okay, for geothermal well, for around 4 megawatts. We have 1 megawatt from reverse osmosis, and we already assigned as a load from the electric grid, main grid, electric grid, 3 megawatts. So we have to produce 4,000 kilowatts. Let's see this effect on geothermal well. Okay, therefore we need this depth in kilometers, around 1,800 feet. Digging pipe hole is 26 inch. Okay, we have geothermal well pressure. Okay, well head pressure and pressure losses through the pipe. Silica concentration. This silica concentration should be around 400 ppm. Okay, and this is the total mass flow rate. This is total mass flow rate from the well, and this is well temperature. This is very interesting. This is the well temperature is 264. This temperature is here. Is number one. This is 264 degrees Celsius. Okay, that's geothermal well. Let's go for the pump. I'm going to. Okay, pumping unit. We have to deal with 487 kilowatts. Let's see this effect on concentrated solar gas engine for the Stirling one. Let's go for the Stirling engine. For 400 kilowatts, we need yes, we need 16 dishes. We need 16 dishes. Okay. We have this concentration ratio. Total plant. We have total solar area is 1,900. This is dish areas. Rim angle ratio, focal length, number of dishes, efficiency of the Stirling, Stirling engine compression ratio, maximum specific volume, minimum specific volume of the engine, of the Stirling engine, piston volume, piston stroke, Stirling pressure ratio, mean effective pressure. It's quite interesting, and the cost of the dishes in US dollar as a total plant cost. Okay, this is responsible for 487 kilowatt for the pump. Okay, let's go for the flash unit. We have to, for the flash, to be sure about this. This is dryness fraction. This is dryness fraction. So it's 20%. 20% the quality of the steam. It's 20% in the flash tank. We are here. Yes, we are here. This 20%. I mean, suppose this is 20% of the steam, and the rest of is water. So we are here. If we goes to this one at this point, so we have 80% steam, and the rest is water. And you can see this or write this in the water. This is mass flow rate of the water. It's around 43 kilograms per second. Okay, and this is total. Total is 54 against 43 is 80% of the mass flow rate is liquid. Okay, and you can discover the tube diameter, flash cyclone height, volume, mass, total mass, and so on. It's a design here. Sure, you can discover some entropies. This is condenser temperature. This condenser temperature. This turbine temperature. This turbine temperature, and enthalpy, entropy, and this is pressure this pressure well pressure, I'm sorry, this well pressure. This is well enthalpy. This well enthalpy, okay, okay, and then density. Okay, for turbine unit, this is mass flow rate of the steam. 20% of the total mass flow rate is just steam, so we have 11 kilogram per second. We can discover this is a dry outlet turbine dryness fraction. It's 80%. Okay, and sure you can discover the entropies, the enthalpies of the outlet and inlet steams. That's quite interesting. Okay. Okay, for the condenser, it's the same. We need 500 surface area of the condenser. We need this condenser tube length, and this is a condenser temperature. Condensation temperature it's around 86 degrees Celsius. This is enthalpy. This is enthalpy with the liquid at the condenser. Okay, and this is enthalpy of outlet cooling water. This is seawater outlet and seawater inlet. Okay, and this stream is going for the reverse osmosis. Okay, enthalpy and mass flow rate and so on. And this is outlet cooling temperature. It's 71. 71. Okay, this stream is going for reverse osmosis. This is thermal energy through the condenser unit, heat transfer, overall heat transfer coefficient, number of tubes or needed, and so on. Okay, we are glad to say that we have such configuration. It's quite interesting. You can change some parameters. Let's go and see if we setting our simulation to the infinity. But first you can discover your data outlets from here. Matlab workspace, you can area condenser, area of the dishes, many parameters you can handle out. Okay, let's go for infinity as a dynamic model. Okay, let's go for dynamic model. I'm going here. Let's control this one. The pressure, the inlet pressure for the turbine unit, and see this effect on the flash cyclone side. Okay, I'm going to emphasize here. Let's watch this on the steam. Okay, we are going to hit run. Okay. Okay, we are going dynamically now. Let's see if we increasing our turbine inlet turbine pressure. Let's see. Yes, this is responsible for increasing the quality of the steam. Suppose I'm going for 50%. Okay, and this you will realize the effect on everything. I'm going for 50%. Let's change the condensation pressure. I'm going for the condensation pressure. Let's increase. Increasing condenser pressure will decrease the quality of the steam generated to the turbine unit. If we increase up to 1 bar. Okay, let's go for but we have to realize that increasing the condenser pressure will cause something in the quality of the steam. Yes, the quality of the steam through the turbine unit, it will affected by this one, by this. Let's see here. Let's stop and collect our results. I'm going to collect it. Okay, let's see here. I think this is the final run. Yeah, okay, this is the, yes, this is the depth of the well. Okay, You can measure depth of the well. What about well pressure head? This is silica concentration will affect. This is well temperature. Yes, if you increase if you are going to increase the pressure of the turbine, so that means that you are going to dig more and increase the depth of the well in order to gain more and more heat. Therefore, we are going to increase the temperature of the well from 200 up to nearly 400. It's up to you, up to your design and so on. This is the pumping work. It's affected. This is condenser pressure, as you can see. We increased it and decreased it. Let's go for, I'm seeking the dryness fraction. Okay. Okay, this is a dryness fraction. Yes, increasing and decreasing because we controlled the steam the steam pressure goes to the turbine unit and the condensation pressure, removing the heat from the turbine unit. And this is outlet cooling water temperature going to the reverse osmosis. We have to keep this not more than 50 degrees Celsius, as I think. And this is well pressure. It will affect, sure. This is well pressure. Okay, you have many parameters to address in this exciting model. Now let's go and see how can we download this model. Okay, let's in search type RITS library. Okay, and see. Okay, renewable energy system. This is this one. Okay. Okay, this is our website. Okay, this is our website. So yes, you can chat with us if you would like. And let's go and see. I'm sorry. Let's go and see how can we. You can go from here for GDS, Geothermal, or Red Shop, or you can click here. You can go to the main library of models, and let's go for. I'm sorry, we have to deal with this. I'm going for yes, single flashing. Yes, this one. Single flash steam geothermal power plant for reverse osmosis. You can click on quick view, or you can click on the model itself. You can click here. Okay, this is a brief description about the model. You can share your model on Facebook and so on. You can add to cart. Okay, and you have to. This is one. Just one item to the cart. Okay, you have to go and view your cart. Okay, and you can click on check out with PayPal. You can, if you don't have PayPal account, you can click on this too. Okay, now okay, if you have account for PayPal, you can easily log in and pay. If you if you don't have, you can pay with debit or credit cards. You can choose your country, as you can see here, and type your card number, your name, and your address. Okay, and your email is very important because you are going to subscribe to us in order to get our notifications, updates, videos, and so on. And also you can create a PayPal account, or you can just continue and you will find your file downloaded automatically after you finish this payment process. Okay, in this model, it's quite interesting. You can edit this model. You can remove some units. You can add some units. You can take some streams from the current streams and create another or add another unit. You can remove reverse osmosis or concentrated solar gas engine cycles, and you can just assign it as a constant block in Simulink, and you can type your input easily. Okay. Finally, don't forget to download our host gas cycle for thermal desalination, MED, and multi-stage flash. It's quite interesting model. And thank you for watching. Let's Don't forget to like, share, subscribe. Thank you.